Good evening, ladies and gentlemen. It's nice to see that people are watching tonight. My name is Gary Johnston. I am the just newly elected Vice President for Scotland for RMETS, and I'm here to welcome you. This is our first virtual meeting in Scotland, so it's quite a challenge. It's also my first meeting since being elected, and it's a bit of a test for us, but I hope you enjoy the talk tonight. There are people behind the scenes working away and making sure the presentation is as functional as possible. We've got a number of people, as I say, from the Society. We've got Samantha working in the background, very grateful for her setting this up tonight. And we've got Vicky, who is the immediate past Vice President for Scotland, who is really trying to help work the technology as well in the background. Right, in saying that, again, it is nice to see people coming on to listen to the talk tonight. And I'm very pleased to welcome to Scotland Professor Yulong Ding. This is quite a coup for us. Professor is a very eminent scientist, and I'll just give you a bit of a background. We did send out a bio, but in actual fact, Professor Ding has got a very, very impressive background. I'd just like to read through it. So if you bear with me just a minute, I'll just give you a bit of his background. Professor Yulong Ding is the founding Chamberlain Chair of Chemical Engineering at the University of Birmingham and Director of Birmingham Centre of Energy Storage. He's a newly elected Fellow of the Royal Academy of Engineers, an elected Fellow of the Institution of Chemical Engineers, a Chartered Chemical Engineer, and a Fellow of the Royal Society of Chemistry. He invented liquid air energy storage technology and led the initial stage of the technology development and validation, which has been commercialized by Highview Power, a UK engineering company. He developed a composite phase change material for thermal energy storage and associated large-scale manufacturing technology, leading to large-scale commercial applications. He has received many awards, including 3 IChemE Global Awards. He's received awards from Distinguished Energy Storage Individual Award, Cryogenic Energy Storage Research Chair Award, Energy and Environment Award, and Technology Innovation Grand Prix Award. He has published over 450 technical papers, filed over 70 patents, and co-founded Dispersa Limited, and more recently, Kelvin Technology Limited. He currently serves on a number of panels and committees, including IChemE Publication Medal Assessment Panel, European Technology and Innovation Platform Working Group on Smart Network for Energy Transition, the Royal Society Net Zero Control Panel, Steering Group of the Royal Society Study on Long-Term Large-Scale Energy Storage, and UK Molten Salt Advisory Committee. So we're very pleased to welcome Yulong along tonight. And just before we switch over to the Professor for his talk, could I just say that if you look to the right of your screen, there's a section called Poll. We are asking people if they could just indicate after the talk whether they are members of the Society or if they are guests. So, Professor, over to you.
Thank you very much, Gary. It's a great pleasure to be able to given this opportunity to talk to you about a specific energy storage area called cryogenic energy storage for contributing to a net zero carbon future. And that's the scale of I'm going to talk about. It's a bit of background and the technology and how we might use the technology for the future net zero carbon future. And finally, have some concluding remarks. So if we look at a sort of first bit background is that global final energy consumption is shown in this diagram. One can see that about 51% of global final energy use is in thermal form, which is heating or cooling. And the transport only use is about 32%, and electrical energy is 17%. And of the thermal energy, which is 51%, only 10% of that is from renewables. Clearly, thermal is important and one of the most important energy for our human life and society. So if I sort of say a little bit more about how we do with energy use. So this diagram is from International Energy Agency, which is although it's a 2016, but it's not much change over the last few years. And you can see the left-hand side is the amount of energy input into the world, and the right-hand side is energy delivered to the end use. So you can see the apparent efficiency of that process is only about less than 50%. Again, so the efficiency of energy use is indeed very low. And if I look at sort of how we use the energy in the UK, so this actually is the amount of energy as a function of time of the last few years. And 2019, we also have the number, and 2020, slightly different, but I think the pattern is the same. So the top part is about gas for heating. The middle part is about transport. The lower red one is electricity. So you can see that the heating using gas is the most important part. So it's the main challenge because the variation of that, and which you can see in the table I summarized. So the summer, winter is very big changes, and but electricity and transport don't change much. So this is in the energy term. If we look at the energy consumption in the power term, which means is energy per unit time, we have similar. So basically, the green ones are for gas for heating, red one for electricity. Again, you can see the thermal energy is the main challenge for the future decarbonization. Let me just bring you to attention to the global distribution of renewable energy. So you can see the solar energy distribution on the left side, the wind energy on the right-hand side. So the red one means we have a good radiation from sun, and a cold part, which is you don't have much. So basically, the conclusion we have from this diagram is a global uneven distribution of renewable energy sources, and also the nationally, and regionally, there was a mismatch between renewable energy supply and the sources, and make it even more difficult to use the renewable energy. So this is actually showing the UK, and also the right-hand side is China, which is the biggest pollution country. So you can see the renewable energy sources are far away from load centers, which is for the UK mainly in southwest. In China is southwest and east as well. So again, posing lots of big a threat, the challenge for the use of renewables. So let me just tell you something about the emerging technologies for energy area, and something which people have not considered, or they have considered, but choose not to say it. So probably you all know that, although we are in a different area, but I'm sure you have heard about electrification of transport, pure electric vehicles in the future. So I did a sort of simple calculation from the primary energy sources, like the coal, the fossil fuels, or wind, or solar. So if we turn this sort of primary energy sources into electricity, the efficiency is about 40%. The 60% of that turns to heat. If then you store electricity and using batteries, that's the probably highest efficiency for storing energy. The efficiency is about 80%. Actually, probably it's lower than that, and which means 20% turns to heat. Then you use the stored electricity for powering an electric vehicle, efficiency probably is at 80% as well. So if you sort of multiply those, so you get sort of overall efficiency from primary energy sources to sort of driving a car, it's less than 30%. Bear in mind, if you look at the right-hand side, for electric vehicles running in winter, cold winter, the range is halved. By range is the range you are told by manufacturer. Actually, you can't achieve that range. The reason is that about 50% of battery power is used for heating. So those are real numbers, actual numbers from the the statistics, which is that you can find from a website. I just put them in a diagram. So basically, half of the battery power is for heating. So again, this efficiency is not very good. So, and what about hydrogen economy? So people have been discussing hydrogen economy for many years, and 50 years, even longer. So if I do the same thing from primary energy sources, produce hydrogen using electrolysis, for example. So we produce electricity first, we turn electricity into hydrogen to storage, and then for use hydrogen fuel cell for driving a car, for example. Then you have, if you work out it, less than 10% of actual primary energy is used for driving a car. The rest, more than 90%, turns to heat, waste. So here, I must say, this is not for criticism. It's just for try to point out the things which they have not considered, and just try to work with develop new technology for make use of those waste heat. And also these actually indicate the something called multi energy vector approach is important to make use of that. So what about very popular ideas about carbon capture, storage, and utilization? And so what I can tell you is that for fossil fuels power generation, you need to spend about 10% of the electricity generated for carbon capture storage. So basically, in other words, so the electrical generation efficiency will be reduced by roughly 10%. And when you capture CO2 and you transport CO2, you need to spend energy, particularly electric energy. For example, you have to compress carbon dioxide to a higher pressure or liquid form, and you need to transport. That would mean another 30% of electric energy turns to heat. So there's quite a lot of loss here. So people don't talk about it, but actually we have to consider those from a whole system approach. What about other things, the new technologies like the electronics, telecommunication, 5G, artificial intelligence, autonomous vehicles? So I can tell you those systems are highly energy intensive globally. So roughly 30% of electrical energy generation will be used, have been projected to be used for data center cooling and telecommunication cooling as well. So it's big. This is not far away. I mean, 2030 and to 2040, and think about 30% of global energy, electrical power generation to be used for data centers, telecommunication, and so on and so forth. Of this amount of energy, electricity, 40% turns to heat. Again, we have to use thermal energy, including heat, which is important to remember. And the next I'm going to tell you is the main topic about cryogenic energy storage. So I'll bring you through the principle and the technology development history, and I'll talk a little bit about thermodynamics and of the technology, and look at the world first cryogenic energy storage pilot plant, some of the results and their implications, and I will make some comparisons for that as well for you, how that compared with other technologies, and what's the cost implications, and also what's space needed for installing this technology. So that's what I'm going to do. So first about the, before I talk to you about that, so maybe sort of I'll tell you a little bit about the, what the category of energy storage. So there's many energy storage technologies. You know the batteries, you have pumped hydro, which is pumping water to a higher hill and then drain water down and to drive a hydro turbine to produce electricity. That's a pumped hydro. You have batteries, lithium-ion batteries, nickel-based batteries, and so on and so forth. And so cryogenic energy storage is actually part of or subcategory of thermal or coupled thermal mechanical energy storage technology. So so what's the current situation in the world. So this diagram, if you look at the left side, is about global energy storage installations. What's the status of that? So most people would use the data on the left side. Basically, pumped hydro takes more than 94%, roughly 94% of global installation, and which is about sort of 185 gigawatts. The rest, only about sort of 11 or 12 gigawatts, is for the rest of storage technology, like a mechanical, like a thermal, like a batteries. So of these, actually, so currently pumped hydro clearly is dominant, 94%. The non-pumped hydro, but only about 6%. That's what most of people would tell you. So this data, I must say, they are not complete. So I've done some analysis and also data gathering. So the right-hand side is actually what I've got. So basically, the real number, or even sort of I can say the close to real number, is that pumped hydro takes about 90%, 10% for other technologies. Of the other technologies, the battery takes only 21%, which is very popular at the moment. And mechanical thermal takes more than 78%. So this is important to bear in mind. So the data published in literature and websites, they're not necessarily correct. So because those data are gathered by different people from different areas. So that's first I want to tell you first. So there I'm going to sort of say a bit about the principle of the technology. So the cryogenic energy storage is a collection of technology using cryogenic material, which can be liquid, can be solids, can be other stuff as storage material. And I would use the Liquidaire as an example to tell you the principle. So basically, when you have excess energy, you have more energy you can't use, or when energy is cheap, what you do, you store energy. In this technology, you liquefy air by using off-peak electricity or renewable energy, and so liquid air is a storage medium, and so the way air is liquefied, basically you compress first and then expand. You use a refrigeration loop to turn air to liquid. So liquid air has a density of about 850 kilograms per cubic meter, which is a lot lighter than water. Water is about 1,000 kilogram per cubic meter. So you can have a sort of feel about what liquid air looks like. It looks like water, and it's lighter than water. And so when you have but the temperature of liquid air is minus 196 degrees, roughly about that. So you store liquid air in a tank, which is insulated. And if you need electricity, what you do, you vaporize liquid air because it's very cold, minus 196 degrees C. Ambient air is, let's say, 15 degrees C, or even it's minus 20 degrees, it's still much hotter than liquid air, which is minus 196 degrees C. So you use ambient air to heat it up first, and then liquid air will vaporize. And because, as I mentioned, so when you produce liquid air, you have to compress air. When you compress air, you produce compression heat. We store heat there, and that heat will be used for superheat the gaseous air and to so that we at a higher pressure, roughly about 100 bars, and they drive a turbine to produce electricity back to the grid. So when you vaporize liquid air, because you have lots of cold, what you do, you capture the cold and store the cold here and recycle the cold back to the refrigeration loop. And hence, actually here you have 3 stores. One is storing liquid air, which is the main store for electricity. And you store the compression heat from compressors for increased power output from turbine. And also you recover waste cold and put it back to the system. So it's a quite integrated system and quite good efficiency. So you might ask, what's the efficiency, run-through efficiency, which means from electricity to electricity? This is about 60% because of compression turbine and those things consumes energy. So and hence you only have if you input 1 kilowatt hours of electricity, you only get 0.6 kilowatts hours electricity out. Is this low? No, it's not very low, and it's actually competitive with lots of other technologies. And the reason I'm saying that, this is for very large scale systems, and it can still have such a good efficiency. And industrial leads, if you look at the industrial companies, grid, the electrical companies, if you can get over 50%, then in a cost-effective way, then this will be sufficient. So that's why I say it's good efficiency. Of course, we can improve it. I will tell you later on when I have time. So actually, the technology of storing liquid air as energy is not very new. And if you look at this diagram, it's a certificate of shareholding, from over 100 years ago. And so this is that time people try to develop a technology for using liquid air to power motor vehicles. And but because of petroleum and which replaced it, and this technology didn't take off. But actually, the concept has been there for over 100 years. So but that's only used as a fuel. They have not used that for storing large-scale electricity for peak shaving, for example, for the grid. So this diagram actually shows you the technology development since I was started to work around 2005, and I was started and then build small system, 15 kilowatts, then 35 kilowatts. Then around 2008, we built 350 kilowatts and 2.5 megawatts system, and around 2015. Highview start to build the commercial demonstration plant in Manchester, which is a 5 megawatts, 215 megawatts hours commercial system. And this is with a Viridor biogas site. And the good news is that last year and to this year, Highview has got investment from a Japanese company, which is about 40 million investment. And also they start to build commercial plants. So they're building one, they're designing and building one in Manchester, and they're designing building one in US. Two of them, and each would be about 50 megawatts. It's a very big system. And in Manchester, the capacity is 250 megawatts hours. In the US is a lot bigger. So the overall investment of that is over 200 millions at the moment. So that's a brief history. So of course, in the process, the proposal of or suggestion of using liquid air for grid scale storage actually was proposed in 1977 by Newcastle academics, but that was only analysis, has never been able to put into use or demonstrated. And also then Mitsubishi and Hitachi, two Japanese companies, will also look at that, and they have never been able to build anything we have today. So that's a brief history. Of course, there are other companies interested in that, like BOC, like Air Linda, like some other smallish companies. So that's actually the full story about the history of that. It has taken about 15 years to get from concept to commercial demonstration and to products today. So it's a long time. So again, this one is just showed as I just mentioned. So if I start, this is actually the left side is the first pilot plant built in London, and around 2013, the pilot plant was moved to Birmingham to just behind my lab in Birmingham University campus, which is quite small actually. Of course, there's different here, which is there's a tank in the middle, which is for thermal storage. There was no thermal storage in the first in London site. So this is today used for research and development in my group and as Manchester group, and so that's just let me just tell you a little bit about thermodynamic basis. This is very simple actually. So if you look at this diagram, so the vertical axis is the availability of energy, which means a portion of thermal energy which can be used for produce power, and the horizontal axis is temperature. So if we use ambient temperature as a reference, so there are two lines. One goes to hot side, high temperature side. One goes cold side, cold side. So you can see, so the availability of energy for cold side is higher for a given temperature difference with reference to the ambient temperature. So for example, if I take about 150 degrees as an example here, you look at vertically upwards. So basically, the availability of energy which can be turned to initial state is about 40%. If you look at the hot side, it's only 20%, which means cold energy is more valuable than hot energy. And if you look at the mechanism, so when you turn a matter to cold side, the kinetic energy of molecules decreases, but the entropy also decreases because the molecules become more ordered. If you go to hot side, it's all the way around. And linking those two, you can see that entropy plays a big role here in terms of availability of the energy for that can be turned to inertial state or useful energy. And if you look at the the conventional physics, so basically this is the lowest point is the ambient temperature goes hot side and goes cold side, and this is different. Hot side is easier, cold side is more difficult. So that's the principle and the thermodynamic basis. So I'm not going to show you equations. So let's probably simply illustrate why we do cold storage. Of course, you produce the energy needed for produce cold energy is higher, but at the end of the day, is overall efficiency. So, and I'm going to tell you a bit about the world first pilot plant, which is 350 kilowatts and 2.5 megawatts hours, which are sufficient to probably powering about 100 homes, so for our day. So it's in our campus, and actually today is still the only one which produces Liquidaire and produce electricity. Still working. So I think the first what I'm going to tell you is that for any storage technology, if you can store and release quickly, then it will be more valuable. And for example, the frequency regulation of power grid, which means to support the frequency at 50 hertz, otherwise the system will collapse. So is the response speed. So that's why I'm going to tell you first, how quick the plant can be started and how quick plant can be stopped. So this is the testing results. So the vertical axis is actually the output power of the turbine, and horizontal is time. So you can see we can quickly start and quickly shut down. So if we sort of slightly enlarge that part, so if I go back, sorry, this is about 2.5 minutes. So because of the animation can't made. So they shut down even quicker, probably about a minute. So which means you can start up very quickly in 2.5 minutes when you have instruction from the power grid you want to support the frequency, for example. So, and as I mentioned, this is actually a diagram which is showing, about frequency regulation of power grids. So vertical axis is about frequency. So when you sort of fall below about 49.8, you need to support. So basically, you have to sort of react very, very quickly. The frequency regulation have about 3 stages. So the stage 1 is that you have to react within about 10 seconds, 10 to 30 seconds. This is called primary regulation. Then the secondary regulation is about sort of 30 second to 30 minutes. And the shorter the response time, the more valuable, and the power grid will give you more money for doing that. So that's why I'm saying that. So although I have said liquid air storage has a response time about 2.5 minutes, there is a specific mode of operation of the plant. If we use something called spinning generation, then the response time can be seconds, which means we can do primary frequency support for the power grid, which is more valuable. So I think I should move on. And the second result is about the use of waste heat. Actually, because liquid air stores energy at minus 196 degrees C, we can actually use the waste heat or renewable heat from ambient or from renewables, from whatever other places for increased efficiency of power generation. So basically, you heat the gas after before the turbine, and which can give you a bit more sort of power output. So we found that using this technology, every 1 degree C you can increase from environment, from renewables, you can increase power generation efficiency by almost 0.5%, which is significant. And there's no other technology we can do that. There's only this one. So that's why I'm saying this technology can be integrated with lots of other emerging technologies I talked about, because there are lots of waste heat, and this can be integrated for that. So another one is that I think probably those numbers may sort of not mean much to some of you or most of you, because we are in different communities. But I think the space requirement for the technology probably makes sense for you guys, because we don't have much space for putting things. And actually, liquid air storage or cryogenic energy storage is quite energy dense. For example, these numbers are sort of gives you an indication of space. So if we have a sort of a small pilot plant in our campus, it's only about 600 square meters. And think about that. This is not packed well because it's in campus for research purposes. So they are not packed. And if you look at 5 megawatts, about 1.5 megawatt hours, which is more than 10 times that space on about 1,000 square meters. And if you sort of look at 20 megawatts, 80 megawatt hour system is only 1,600 square meters. And that include car parking, a few car parking space and offices. And if you look at the big ones, 200 megawatts and 1.2 gigawatts hours, that's only 16,000 square meters. So it's very compact. So, and of course, most of you will be looking at sort of cost. So I'll spend a little bit of time to explain that. So this is sort of roughly the cost. So here you have a first of its kind, which is the first you're building. And then, in terms of cost, the power, which is kilowatts, and the kilowatt hours, which is the capacity, and the tenth of its kind. And, in terms of the investment, in terms of the power, in terms of capacity, which is the kilowatt hours. So, and if we assume you do 1 cycle a day, and then you can see that, towards that side, the bottom right side, you can see the cost reduce a lot with with time, with scale. So large scale costs less. You produce more units, the cost is a lot less. So the key figures here, for tens of units, the 1 kilowatts hour, 1 kilowatts of the system would cost about 600 pounds, and 1 kilowatt hour will cost about 162 pounds. These are a lot lower than battery system, so a lot lower than other things, and comparable with pumped hydro, which is the most popular used energy storage technology today. So, and another thing is that to compare that with other technology using something called a level cost of economic cost, which is of course we have some assumptions for that, and the vertical is sort of basically the cost per megawatt hours electricity. If you charge that amount, that you will make money. So horizontal axis of different technologies, you can see the three lowest technology is pumped hydro, compressed air, and liquid air. So the rest is a lot higher. So that give you, of course, those are not very accurate, but the order of magnitude is correct. So those give you some idea of how the cost of technology compare with other technologies. And also, I'm telling you something which is the actual cost from pilot plant to pre-commercial and to sort of a large scale. So that's the sort of actual numbers here and here. Then the bigger one will be somewhere here. So basically, you can see that the cost, which is similar to what I just talked to you in the two tables, so I said I'm going to tell you how the technologies compare with other large-scale technologies, which one is a compressed air energy storage, which means you compress air when you have excess electricity and store compressed air at a high pressure underground somewhere in cabin, for example, and pumped hydro on the right-hand side. When you have excess electricity, you pump water from lower reservoir to higher reservoir and use a hydro turbine to produce electricity. So it's the most popular and the large scale already in applications. So this is a table which shows you the comparison from energy density, from lifespan, from efficiency, from cost, from cost that you should charge customers for use that, and storage time, and geological conditions, and technology maturity. So basically, pumped hydro remain the most competitive, but liquid air is competitive, competitive with them as well. So we can see the energy density of liquid air is 660 to 120 times of pumped hydro, which means space requirement is a lot lower, and round trip efficiency can be comparable with pumped hydro, and the costs are comparable as well. So, and also one important feature of liquid air storage or cryogenic energy storage is that there's no geological confinement, basically. But compressed air and liquid air, they are limited to sites where you have a mountain, you have two legs, and for compressed air you have to have cabin, or you have to use big tanks, which are not economically viable. So that's the main advantage of technology. So I'm going to spend probably a few minutes just explain the cryogenic energy storage for net zero carbon future. So the first thing is about sort of how we might use that for future net zero carbon conditions. So this diagram shows the offshore liquid air-based technology or cryogenic energy storage technology for offshore renewable energy transportation and storage. So I should probably say a bit of background of offshore renewables, for example, offshore wind. And I know Scotland has a lot of offshore wind, and so does the England and also Wales. And so, of course, Scotland has most of those. So the current technology uses, you have offshore wind turbine platform, and you have a transformer, and you have a conversion steps, and also the turning electricity to a higher voltage using high voltage AC or DC, which is a direct current or alternative current for the transmission using undersea cable to onshore for onshore utilization of electricity, which is quite expensive, and also the lifespan probably about 15 years, and the maintenance costs are very high. So we have been developing a technology for that using Liquidaire. The idea here is that, okay, we are turning offshore wind power to Liquidaire using technologies I just mentioned, and we transport Liquidaire using ocean liners or ferry or barging ships to move to transport that to onshore, and then we generate the power from onshore. Of course, you have to still look at the logistics, but I mean, this is pretty much similar to liquefied natural gas transportation, and hence technologies is a high technology ready level, which can be done fairly easily. And so by doing so, we have done sort of economic analysis. This technology can be between 20 to 40% cheaper in terms of capital cost. And also because we use Liquidaire, you have storage function, and hence it's more flexible, and the power grid is better, likes that better than the current technology. So because we already have storage function, the investment, the capital investment actually is even a lot lower than the current technology, because current technology you still have to use batteries to back the power. So because of a fluctuation of renewables. So that's one aspect. So based upon that, we developed the concept further, which is I call the sort of a net zero carbon future, which is basically we use a Liquidaire or offshore Liquidaire or cryogenic fluids as a platform. So basically we produce either Liquidaire or ammonia or hydrogen and from offshore platform, and we use shipping rather than other things, and for level support for cold chain. Actually, because Liquidaire has a temperature of -196 degrees C, we can use this cold for liquefying natural gas, offshore natural gas, so that you don't have to have a offshore platform for a gas turbine to produce liquefy natural gas, because that is a carbon intensive. So and of course we can do cold chain transportation, uses the cold, and for fish, freeze fish, and for shipping fish globally. And of course we can use the Liquidaire or ammonia or hydrogen for zero shipping, and so on and so forth. So this outlines the main idea. So with that, actually, I'm have a sort of a confidence. I mean, the future is good. Future UK could be a net energy exporter, where we can ship renewables using this sort of method globally to other countries. Of course, we can ship in a similar way from other countries to us, and so it's a global shipping of renewables. Probably will become a future big business area, and I know the Shell, BP, and other companies are sort of interested in this sort of methods, and we are also talking to some of the companies for developing that concept and doing future demonstration. And so finally, I'm going to conclude my talk by, first of all, that global energy use, more than 50% of that is for thermal form, which means thermal energy is important. The challenge is bigger than electrical and transport related decarbonization challenges, and efficiency of conventional energy conversion and transmission technologies is low, and most loss to heat and efficient use of heat is important. And thirdly is that little attention has been paid to pitfalls in new and emerging technologies. And for example, electrification transport, hydrogen technologies, telecommunication, and artificial intelligence, carbon capture storage, which are highly energy inefficient. And I think multi-energy vector approach would provide a potential solution. And Liquidaire-based technology falls in the thermal energy storage category and is highly competitive in terms of technology. Maturity, easiness of technology to implement, and space requirement and geological limitations and the costs. And the cryogenic energy storage or Liquidaire energy storage provides a multi-energy vector solution to future a net zero carbon energy system. And that's all from me. And thank you very much. And this is our new Birmingham campus. And if you do have time, welcome to our campus and look at our pipelines. Thank you very much. And that concludes my talk.
Professor, that was absolutely fascinating, and I see there's a few questions coming in. It really is an interesting topic, especially at the moment when we're seeing so many people looking at different ways of alternative energies. One question I would ask myself is, when you're looking at the economics of this plant, is there a maximum and minimum size? Is there an upper and lower limit to the size of the plant before it really becomes economical? Or is this something we could see in a village scale as opposed to a city or county scale?
This is a very, very good question, and I have not talked about that here. So basically, yes, there is. For the standalone system, which I've been talking about, and which is a HiView is building at the moment, there is a minimum scale, which is technically it's about 5 megawatts. Economically, probably it's about 10 megawatts upwards. Smaller systems wouldn't work for standalone system. The reason for that is the liquefaction of air works for large scales. Small scales is very low efficient. And having said so, over the last about 3 or 4 years, we have developed a small scale system, which I have not talked about today. I call it Liquidaire for combined heating, for combined cooling, heating, and a power system, which actually make use of waste heat from compression a lot more efficiently. And that efficiency can go to about sort of 75, 85%, even a lot more efficient than current standalone large-scale system, because we make use of heat and cold, and also we don't mind about low efficiency of air liquefaction process, because by low efficient liquefaction I mean the system produce lots of heat, and we can use heat for communities and for big buildings, and in that way we can work upon sort of even several hundred kilowatts systems. So for communities, for small villages, and hopefully that answers your question.
Yes, I think it does, and I see that somebody's asked a similar question. Another question from John. In that the UK government policy is based on a wind energy, is the method aimed at exporting this intellectual property methodology aimed at support and development in the other world access areas with UK specific and government support, scientific and government support. Sorry, I'm having a problem with the screen here. I'll read that again. In that the UK government policy is based on wind energy, is this method aimed at exporting the intellectual property methodology aimed at support and development in other world areas with UK scientific and government support?
I think it's a very good question, and I mean, even me initially, many years ago, I was still quite dubious about sort of UK policy for that. I mean, we know UK is very good at innovation, and discovery, and lots of technologies started from here, but then end up commercialized in other countries, particularly in the United States and even Europe. And over the last few years, probably a small number that probably went to Asian countries, particularly China. And so it's a fairly sort of a sensitive time to talk about China and the US, but actually that was the case. So gradually, actually, I sort of find out sort of because the UK is a fairly small market. Businesses only doing business in the UK are difficult to survive. That's one of the reasons. I think but I think it's good to have a sort of a headquarters of the companies in the UK, and keeps the IPs in the UK and license all sell products or whatever you license the IP to companies either in the UK or other countries. So that's probably the best way. That's actually what I have been doing, and I have several licenses to overseas companies. Although some of those has not sort of started to return, but that's hopefully in the future. So it's difficult to balance, and also particularly for the general public, because they're probably not sure how UK might benefit from sort of licensing or the giving away some of the IPs. But I think at the end of the day, it's economics, and not only from immediate future, but also from the strategic aspects in the future, so that's my view, but not sort of represent my university or sort of. So,
thank you. Right, we have a question from Brian. Can this technology be a way to replace our reliance on fossil fuels, thereby reducing our carbon footprint in the production of electricity?
My answer is certainly yes. If we have use all renewables, we store renewables, and if we store sufficient amount of renewables, yes, we can. And but the question is that how much we need to store for how long time. And actually, Royal Society is doing a study, which I'm on the steering committee, as Gary mentioned. So what's the actual storage capacity we need for long-term storage for net zero scenarios using all renewables. Of course, we have to consider other generating technologies like nuclear, like a sort of biomass as well. So I think it can be, and but I can tell you sort of the number I know so far, which is not the final, might not be correct, is we need sort of roughly about tens of terawatt hours, something like between 50 and 70 terawatt hours will be needed, which is huge. So think about our sort of pumped hydro storage capacity is only gigawatt hours. If we multiply gigawatt hours by 1,000, that's a terawatt hours. So it's massive. So yeah. So hopefully that answers this question.
Thank you. One from Alan. Are there plans for more plants to be built?
Yes, for large-scale plants, as Highview has quite a few things in their book. So currently 2 confirmed. One is for in Manchester, UK. It's a 50 megawatts, 250 megawatts hours, and the one in the US is also 50 megawatts, but a lot bigger in capacity because they store longer hours. So the others are not confirmed or still in maybe confidential stage. And also in parallel for that large scale system, I'm working on building smaller system for combining cooling, heating, and power. And the first one is unfortunately it's not going to be in the UK because I'm struggling to find the investors for building one in the UK. Although I made big efforts try to work with people in Scotland, particularly the Scottish Islands. It's difficult at the moment, I think. But the first one is likely to be done in overseas. But IP in the UK, I can assure you. So.
Okay, another question from Katrina. How would the efficiency change with ambient temperature, e.g., between here at 20 degrees C and the GCC at 50 degrees C?
So could you repeat this question? I missed the first sentence.
How would the efficiency change with ambient temperature, e.g., between here at 20 C and the GCC at 50 C?
Okay, so the changes is probably slightly. It's not much, but probably as I mentioned. So if you think about 1 degree C increase in temperature, will give probably 0.5% of power generation efficiency, as I mentioned. So 30 degrees C difference. So would it be you have an increase by between 10 and 15%, which is quite a big. And I think if I sort of might be sort of people may think that's a sort of over optimistic because there's a balance here, which is I did not mention, is the storage of heat from compression costs money, and if you have waste heat from surrounding area, you don't spend that money to store, and hence you can still have efficiency. That's why there is balance there. So yeah.
Okay.
Sorry.
Thank you. Right, we have one from Shona. Are there logistical challenges associated with building an installation like this offshore, given its need for a large area? Do you see scope for this being used on land, e.g. next to wind farms where there is no pumped hydro, or next to substations as a sort of overflow protection for power surges?
I mean, my answer is clearly yes, and actually the Highview, the build being done by Highview, which is actually at substation, and which according to their sort of business model, I think, which is more around substation region, because for large scale systems, either between the transmission and also the distribution network part. So, and for small wind farms, I think the system I'm mentioning for combined heating cooling system probably and power probably is more suitable if scale is small. Of course, that needs to be sort of not far away from community, which is or from factory which need heat. So if there's no such community, then efficiency will be reduced. Then they eventually will be determined by the cost benefit. So what I know is that National Grid pays wind farms not to generate in the UK. They paid either a few years ago was tens of millions, several tens of millions, and 20, 30, or 40 millions. Over last year, it's a lot higher. So I think there is a case for that.
Okay, thank you, Professor. I think it's been fairly representative of the questions asked. And I would like to thank you very much for your talk tonight. It was absolutely excellent. And it certainly was eye-opening, and it looks as if it's going to be a very interesting future for this technology. We certainly should be keeping an eye out for it and look forward to seeing advancements in it and to being plants being actually built. So again, I would like to thank you very much for your talk tonight on behalf of the Scottish Centre. I would also thank everyone who has participated tonight and joined in and listened to Professor Yulong Ding. And I would hope that you've all enjoyed this. At this point, I would be asking for a round of applause in the usual way, but as we're on cyber, I don't think you're going to hear them all very loudly. But I'm sure that you will understand and appreciate our thanks for you preparing this and giving us such an excellent production tonight, excellent slides. Just before we finish up tonight, I would like again to thank Samantha Hargreaves and Vicky Ingram for the behind the scenes work in organising this tonight. And we would encourage people to become members of the Royal Met Society. It's a very worthwhile organisation, and I think a lot of people will benefit from it. I would encourage you to become a member. Watching and participating in our program is free, and we don't charge for that. We have some really excellent speakers, and we have a program, and I would hope you would take note of that we do have an up and coming program, and we will look forward to seeing you all again at our next session, which is in November. Yes, you see them coming up on the screen on the 6th of November, and this is by Daniel Brunner. Daniel is actually a member of our committee in Edinburgh, and I hear him speak all the time. I think he's absolutely excellent, worth tuning in. So I would encourage you to come along to our next talk to listen in. I hope that you haven't found this too difficult technology tonight, and I would bid you good night and hope that you have a good evening for the rest of the evening. And again, once again, Professor, I would thank you very much for your time tonight and the effort that you put into preparing your slides and your talk. Thank you very much, everyone.
Thank you. Thank you very much. My pleasure. Bye-bye.
Bye-bye. Thank you.